Okay, that's good though. That's as long as I know where you guys are coming from, because you guys just, oh, you mean ohms, you mean this? Like, okay, I'm assuming you guys know something about it, so I don't want to be too remedial at the same time.
I've applied Ohm's law a couple of times.
There you go. Okay, so for the second part of the lab, and some of you are at different spots, so I'm just going to start from how we need to approach it. 4.3. Okay, so here's the premise. If I've got a resistor, what is necessary to get current to flow? You need a potential difference because you need an electric field. So you have to have a voltage, or you're not going to have a current flow. Okay? Whether it's connected or not, however it's connected on the outside, I don't care. If you have no voltage, you have no current. Okay? We're going to apply this to our lab to do what's called balancing a bridge circuit. A bridge circuit is basically a circuit with multiple branches. And we want to balance it in a certain way. So here's what our circuit's going to look like. So we basically, on one end, we have a meter stick. And along the meter stick is a long, skinny wire. This is what's true about all conductors. It turns out, and for this, just take my word for it. If you have a conductor, the resistance will always be proportional to the length. Because the longer the conductor, the more of the same material it has to pass through. The longer the accident, the slower the traffic around it. So the point of the variable resistor is that if I were to measure the resistance between any 2 points on it, it would be directly proportional to the length of the wire. Okay. Now here's what I mean by V equals 0, no current. It's a bridge circuit because there are two connections. We have two regions of the circuit, two branches, if you will, but they're attached by this little bridge in the middle. This bar is a resistance. Now, it's not what we're used to, but the cool thing about it is by measuring the length, I'm going to call this one L, I have no idea what I'm using for letters for you guys. I'm going to call this L1 and this L2. It's got two lengths. That's all. Okay? Now here's the thing, and because of that, each of these, there's a resistance for L2, and there's a resistance for L1. And it is purely dependent on their length. Again, more stuff in the path, the more drag and the more resistance. So, we're going to attach two resistors that would otherwise be in series and connect them in parallel with this branch. Okay? What that means for us is on your circuit board, take two resistors and put them in series like you did for the first part with the 3 resistors. But we only need 2 of them. One of them will be our reference resistor. The other one will be the unknown resistor. I should have unknown resistors, but it does not appear that I do, so we'll work around it. The bottom line is this. If I connect the ends, if the voltage from A to B is anything but 0, current is going to flow from one side to the other. It will not flow if there's no voltage between the ends. This end is 5 volts and this end is 4 volts. You're going to have a 1 volt or a tenth of a volt potential difference between the ends. As long as they have the same voltage, no current. So what we do is we put our galvanometer inside, and this will tell us whether or not the voltage between the two ends is the same. So let's think of some examples here. So if this is the minus and this is the plus. And this is 5 volts, and this is 0. If we have 5 volts across this bridge circuit, the ratio of these lengths is related to their resistance. The total resistance from end to end, well, I don't necessarily know what it is. But what I do know is this. If there's my Rx, and there's my R, I guess we'll call it R2. If this difference is 4 volts, one fraction of that voltage will be across this resistor. The other fraction will be across this resistor. If the potential difference across this side is 5 volts, then the potential difference across this segment plus the potential difference across this segment will also be 5 volts. So when the ratio of this length to this length is the same as the ratio of this resistor to this resistor, you should get no current to flow between the two. So as we look at this thing, let me change colors here for you guys. If we have 5 volts from end to end, and I'm going to call this Vx, we'll put numbers in here for now, and I'm going to call this V2. And then I've got these 2 lengths and these 2 voltages. Okay? So here's how it works. If this is 10 volts, and this value is 100, and this is 100 ohms. It doesn't matter what that voltage is. Okay? If I measure this length down here, and this length is 0.6 meters, and this length is, say, 0.4 meters. And I equals 0 across here. This tells me that the ratio of potential difference, Vx, divided by V2, is proportional to the length of the first segment divided by the length of the second segment. And this ratio is basically I times Rx over I times R2. Because it's the same current. Whatever current's flowing through here, it's constant. It's the same here as it is there, if none of it's coming off this way. So we'll put numbers in here. So this goes away. And it's related to the lengths. So when this is the case, when the ratio of Rx to R reference is equal to the ratio of the 2 lengths of the segments in the wire, when you connect it, it's balanced. There will be no current through the galvanometer. In which case, if we rearrange this, our unknown resistor will be related to the magnitude of the resistor we know. And by the way, to use your reference resistor, use your resistor box. That's the easiest thing to do because you know it's 1,000, it's 2,000, it tells you right there what it is. So some of you were using for your resistor and your unknown just picking 2 and reading the stripes. That's fine, but that's why we have a resistor box. It's explicit, it's only 1% uncertainty, it's right there. So you don't have to worry about it. Right? Just make it easy. So the idea then is if we take the ratio of the 2 lengths and multiply it by our known value, that'll give us our resistance, our unknown resistance. So in this example, if R2, our reference resistance, is 100 ohms, and L1 is 60 centimeters, or 0.6 meters, and L2 is 40 centimeters, then our reference resistance, or I'm sorry, our unknown resistance would be the ratio of 100 ohms to 0.6 over 0.4, or 1.5, so 150. That would be how we would use it. It was used in the old days when they didn't have ohm meters and the different things that we have now. So if you have one standard resistor that you know, all you need is one, and you have a uniform conductor that you can vary the segments, then you can use it as a balancing circuit to figure out what the resistance is. So it's a very simple way of doing an ohm meter. And you can even make a simple device to do that for you. So this is, it's again, the measurements are easy. Understanding the subtleties is, that's what we're going to spend Tuesday on. It's so we're a little bit out of whack in terms of our order. But it all comes back to the one premise. When you have no voltage across anything, you have no current. In this case, we want a situation where there's no current across our meter. How we set that up is actually relatively simple. We only need about 4 wires. Maybe 6. Or 12, right? So now let's just think about another situation so we can just just a couple more examples. If instead, if you took 2 resistors, and maybe we give Rx a value. So say Rx were 330 ohms, and R2 were 1500 ohms. What is L1 and L2? We'll look at it backwards. What would L1 and L2 have to be in order for this to be the case? And assume that it's a meter stack. So we'll assume that L1 plus L2 equals a meter. So in other words, if we took 2 resistors here and plugged them in and connected the center between them to some point along here so that we have 2 different sections, what would L1 and L2 need to be to balance the circuit? So what do we know? We know that L1 over L2 will be equal to Rx over R2, or 330, divided by 1500. So it's about 0.2, a little more than 0.2. 0.22? Or, if you will, L1 then should be equal to L2 times 0.22. But what's L2? L2 is 1 meter minus L1. And that should be equal, or that should be, when you multiply it by 0.22, should be equal to L1. So you got to do a little bit of algebra to figure it out. But ultimately, if you manipulate this a little bit, we're left with L1 times 1.22 should be equal to 0.22 meters, or L1 should be equal to 0.22 meters divided by 1.22. I just solved for L1. I think I solved that right. So it's going to be about 20 or 17 or something centimeters, 16, 17, 18. So this should be 0.18 meters. So L2 then would just be 1 minus that, or 0.82. So does that help with the explanation of it?
Yeah, that's good. Much
So-
better.
So to set it up then, you'll need your galvanometer. Can I borrow your circuit board real quick? And your reference resistor. Yeah, that one there. And I won't worry about the galvanometer. Okay, so to set it up then,
Yeah, we have to have,
take your reference resistor. In fact, I don't even know if we need the circuit board coming to think of
we'll
it.
use 100. Just
What is it,
100.
everything?
It's 100. Well, it depends on what
Never got
resistor you're
anybody
going to
today.
use. Your 100, or you can use the reference
the store with me?
resistor here.
So you can plug your thing up in there.
Oh yeah, you're done with the galvanometer, or with the voltmeter.
Okay, we'll use this for 100.
So, it doesn't even have to be 100, but why not, let's just use 100, so set it to 100.
Why?
Okay, and we're gonna run it in series, which means
Record the rest of this.
the two greens are the two ends of the resistor. So we're gonna run one of the greens,
You already set up.
It's not for me, it's just for everybody else.
Close to the resistor then?
well, one of the greens we want to run to one end of the meter stick.
So we're newly added.
Yeah.
That's not, that's not, I don't think that's mine.
You guys.
No, this,
Yeah, that's not mine.
Oh, the bad ones? Okay, perfect.
It's an extra one.
I can get rid of them then.
here's some extra.
Oh, wait, no, this is mine. RC circuits, that's right. Yeah.
Okay, but.
Oh, it
I thought it was
is.
this
It's the next
one.
lab.
Yeah, it's next one. That's right. Yeah, so I'll be that then. So I'll get it done next class maybe.
Okay, now for the second, in fact, as I'm looking at it,
I
have a feeling
I'm
that's
gonna
what
do that
this
lab
is
right
for.
away right now. I'll come back home.
is that this
Yeah.
is
So you can
probably
just start working on this one
non-resistive,
and
it's
turn it
probably
down
on
to
the
the Sunday
process,
open.
but I don't wanna do that, just to
Yeah,
make
fuck
sure.
it.
it's not a problem.
I'm gonna work on it both anyways, it's fine. It's
Yeah, but as soon as I'm gonna you figure it out, just I'm gonna save you some time. Some help me.
yeah, why not? Sure.
We'll talk about it. Okay.